This is 48th lecture, and our topic today is the differential pair, which we started last time, and we add the Gilbert cell. Gilbert cell, a particular circuit which is very popular in integrated circuits. Gilbert cell, both of them can be used as wideband amplifiers. This is what we are going to look at today. The differential pair, as I had drawn the last time, is the first transistor is without a load. It's a common collector stage coupled to the second transistor through the emitter, and this goes to a constant current source, a current source. The input is applied to Q1 VSRS, and the output is taken from Q2. The load is R sub C, and this is the output V0. The Q2 base is grounded. This is the circuit. We made an analysis, we made a qualitative explanation of why this is wideband. Basically, it's a wideband because both CMUs, their teeth have been taken off. One CMU reflects as twice CMU, and the other one reflects as only CMU. It doesn't reflect at all. It goes from collector to ground because the base is grounded. So there is no Miller effect. There is a Miller multiplication in Q1, but it's a very small amount, only twice CMU. And this is the basic reason. We drew the equivalent circuit, and there was a very decent, very elegant result, namely that we had found out V pi 1 was equal to minus V pi 2, which made the equivalent circuit look like this. We had gone through this analysis, so I shall not repeat. VSRS, and then instead of an R pi, there was a continuity, and it is 2 R pi. The voltage across this is twice V pi, because one V pi is opposite of the other. The capacitance here, 2 C pi's in series, gives rise to C pi by 2, and then C mu was reflected. Then you have the GM V pi. One has to take care of the fact that this is 2 V pi, not V pi. GM V pi, and you had R sub C and C mu. This is equal to V0. By simply looking at it, we could derive the result that V0 by Vs is the mid-band gain, let us call it AV0, divided by direction of GM pi is opposite. Yes, thank you so much. In other words, V0 and Vs shall now be in phase with each other. Okay, there is no phase reversal. Wonderful. Okay, by looking at it, we could derive the result that this must be of the form 1 plus S by omega P1, 1 plus S by omega P2, where the values of omega P1 and omega P2 are also obvious. All the three quantities are obvious. For example, AV0, we found out that this is beta 0 R sub C divided by 2 R pi plus Rs. That's it. 2 R pi plus Rs. And that's obvious. GM V pi flows to RC. V pi is this voltage, twice V pi is this voltage, and therefore we found that out. Okay, and omega P1 and omega P2, omega P1 is the reciprocal of this time constant, which is C pi by 2 plus C mu multiplied by what this capacitor sees is a parallel combination of 2 R pi and Rs. So 2 R pi parallel Rs, and omega P2 is simply the reciprocal of this time constant. That means omega P2 is equal to 1 over RC C mu. Agreed? Let me write down omega P1 also, 1 over C pi by 2 plus C mu twice R pi parallel Rs. depending on the values of these resistances, namely R pi Rs and R sub C, omega P1 and omega P2 may differ from each other, may also be comparable. If one of them dominates, that is, if one of them is more than 3 times the other, you remember the figure 3, because squares are involved, all right, then that particular pole shall dominate in determining the high frequency 3 dB cutoff. That is, FH will be approximately equal to FPI, where FPI is the dominating frequency. Okay, it is either FP1 or FP2, depending on whichever is 3 times greater. On the other hand, even if this 3 times greater is applicable and you have the figures, there is no harm in taking this formula 1 by FH as 1 by FP1 plus 1 by FP2. Is this correct? Is this the correct formula, or FH should be FP1 plus FP2? This is correct for high frequency. For the low frequency, it is the sum of them. All right. So you could also apply this formula, or since it is a quadratic, there is no harm in solving the quadratic equation 1 plus omega h squared divided by omega p1 squared multiplied by 1 plus omega h squared divided by omega p2 squared would be equal to 2. Okay. We shall take an example and try to find this out by all the 3 methods and see how good things are. Okay, now let's take an example in which capital I, the constant current source, is 1 milliampere, which means that IC1 equal to IC2 equals to half of this, because it's a differential pair, 0.5 milliampere. That therefore gives GM as equal to 0.5 divided by 25, that is 20 milliampere per volt or millimole. Okay, GM is this. It is also given that beta is 50, R sub C and R sub S, they are equal to 1K both. C mu is given as 2 puffs and Ft is given as 400 megahertz. From these you can find out R pi. Beta is given and GM is known, so R pi would be equal to 50 divided by 20, which is 2.5 K, and C pi can be found out as GM divided by 2 pi Ft minus C mu, and that comes out approximately as 30 puffs. Then the midband gain, no more negative sign, it is in phase, beta Rc divided by Rs plus 2 R pi. If you substitute the values, this comes out as 16.7. And then we calculate omega p1 and omega p2. Omega p1, which is 1 by C pi by 2 plus C mu. This is also remarkable, that instead of C pi, we get C pi by 2. Isn't that right? That also contributes to wide banding. C mu, then Rs parallel to R pi, and if you substitute the values, this comes out as 70.6 megaradians per second. 70.6 megaradians per second. On the other hand, omega p2 is 1 by C mu R sub C, and this calculates as 500 megaradians per second. So omega p2 is more than 7 times omega p1, and therefore FH would be controlled basically by omega p1, and it should be approximately this divided by 2 pi, so many hertz, and this comes out as 11.24 megahertz. Okay. On the other hand, if you use the time constant addition formula, in other words, if you use the formula 1 by Fh equal to 1 by Fp1 plus 1 by Fp2 and substitute the values, this leads to a figure of 9.95 megahertz. One may think that this is a closer approximation to the actual value. It is not the case. You see, we ignored omega p2 and we got 11.24. We brought in omega p2 in this approximate formula. Oh, there is another approximate formula, squared 1 by fh squared. Okay. However, this one gives 9.95. On the other hand, I solved the exact quadratic, solved the exact just to find out which one is closer, and exact solution gives me 11.03 megahertz. You see, it is closer to 11.24, that is by ignoring omega p2. One cannot therefore say which formula would give you more accurate results. One has to find out. It depends on the situation. One has to find out. There is no rule of thumb that you use this, then you will get a better. You must notice that in this example, the transistors that were used, Ft was 400 megahertz, and the bandwidth that we get is only 11.03 megahertz. That's approximately 1 by 40, approximately 1 by 40. Suppose, now this happens because we are processing basically voltage, and it's always true. It's always true. Suppose I had processed current, if current was my signal. This fact was known to people, but it has dawned on people only very recently, because in integrated circuits, the demand for higher and higher bandwidth led people to think that if instead of voltage we do current processing, if we take current as the signal, then perhaps we can reach very near Ft. We can reach very near Ft, and this led to a new group of circuits, integrated circuits, which are called transconductance circuits. And instead of operational amplifier, we now have in the market, in addition to operational amplifier, more modern chips are OTAs, that is operational transconductance amplifiers, and they are basically current processing. Okay. We shall at least have an exposure to one circuit, and this is what I want to show you. It is the Gilbert cell, which basically processes currents instead of voltages. And the idea is the same, that we want to go as close to Ft as possible, and wide banding should be possible. One of the qualitative things that that one thinks in terms of wide banding by current signal processing is that the parasitics which cause distortion of voltage may not have any effect on the current. Okay? It's very qualitative. I am not going into the details of this, but it can be shown that parasitics are less effective in current processing rather than voltage processing. And however, in the practical circuits, the engineer's obsession, because of historical reasons, is with voltage processing. So if I give you a current chip, current amplifier chip, and your need is for voltage processing, so the microphone apparently generates a voltage. It's a high impedance source, generates a voltage. Even some of the electrodynamic microphones, they generate a voltage. So basically you generate a voltage, and perhaps you might like to display it on an oscilloscope, and basically what you display is a voltage. Alright, and therefore what do? If I give you a current to current transducer, you have to convert it into a voltage to voltage by a V to I conversion at the beginning and an I to V conversion at the end. This is not difficult at all. For example, you know that this differential pair, with a small resistance here. Suppose you apply a voltage between these 2 points, between these 2 bases, then these voltages are converted to currents. Agreed? These voltages are converted to currents, and the voltage difference between these 2 emitters shall be proportional to the signal current. Agreed? The difference between the 2 collector currents. You see, application of voltage here will cause an unbalance between these 2 currents, and therefore it will cause a voltage difference between these 2 points. Basically, this is a voltage to current converter. All right, voltage to current converter. And if you want to convert a current to a voltage, all that you have to do is to pass them through a resistance. All right, and therefore it is not difficult. So, if you want a voltage amplifier out of a current amplifier, then you require a V to I conversion at the beginning and an I to V conversion at the end. We will see how the Gilbert cell, it's after the name of a British scientist called Gilbert, Barry Gilbert, that's his name, he's still alive, gave a very interesting circuits based on differential concept, which is very much used in a number of chips. Gilbert must have become very rich after he patented this circuit and sold out the patent. And the only condition for a Gilbert cell is that it cannot be made in discrete circuits. The reason is that Gilbert cell for its operation requires very closely matched transistors, and that can be achieved only by IC fabrication. Let us look at this circuit. I will draw this circuit only in parts, and at the end I will draw the full circuit, and I shall explain as I go ahead. Please try to draw with me. You have a transistor Q1 whose base is grounded. All right, the current here is I1. From this collector is connected to another collector, we shall call that as Q3, okay, and this current we will call as I3, so that this current is I1 plus I3. Where it comes from, it could come from a supply, it could come from a constant current generator, we don't bother. Okay, the other part of the circuit is you have another transistor Q4, symmetrical circuit. You have another transistor Q4 whose base is again grounded, and the current through this is I4, and this collector is common to another transistor Q1, Q3, Q4, so this should be Q2. All right, this is connected to this point. This current we shall call as I2. All right, therefore this current would be I2 plus I4. Agreed? It is a criss-cross type of connection. The two emitters are connected, and this is connected to a constant current generator I sub E. Now the connection between Q1 and Q2. Q1 feeds Q2 and Q4 emitter feeds Q3. Okay? No, it is not. It is not a Darlington pair. Well, it's similar to Darlington, but it's not quite, because the two collectors are not brought together. In the Darlington, the collectors are connected. Q1 and Q2 collectors are not connected. Okay? If it were, it would have been a Darlington pair. Then of course Gilbert could not have got his patent, because Darlington would have objected. Darlington was alive at the time. Darlington died recently, Sidney Darlington. Okay. Then these two emitters, I will show this connected to two current generators. And how these current generators are obtained, I will show in a different circuit. We will call this as IA1, and I will call this as a part X of some current I sub A. We will explain what this mean later. And this is IA2, it is the rest of the current IA, namely 1 minus X I sub A. Some fraction, X is less than 1. Okay. Have you drawn this circuit? Yes, sir. Okay. I will come to this. I sub A is a current generator, and XIA and 1 minus XIA are created by this difference. Normally the two currents would be identical. Normally these two currents would be identical, that is IA1 and IA2 would be identical. The difference or the unbalance is created by a voltage source, and it is like this. This part of the circuit now I shall draw separately. Is this part of the circuit drawn? Okay. The second part of the circuit is, I wanted to show you XIA, how it is derived, and how 1 minus XIA is derived. This is taken to a differential pair. Derived from a differential pair, the emitters are connected through two small resistances R sub E. Okay. And the middle point is connected to a current source I sub A. This is the current source I sub A, which goes to a minus VEE, a negative supply. Okay. Now, between these two bases is applied an input voltage V in plus minus. This is how those two current sources XIA and 1 minus XIA are created. You can see that if these two are tied together, if the two bases are connected together, okay, then this current and this current shall be identical, because these transistors are absolutely identical. We have named we can name them as Q5 and Q6. All transistors are identical. They are made in a chip. It's a chip. All transistors are identical. So what you do is, when you apply a voltage V in here, this causes an unbalance in the two collector currents. And this unbalance, however, the sum of the two must be equal to IA. All right. We assume, of course, that beta is much greater than 1. That is the base currents we ignore, and therefore the collector currents are approximately equal to the emitter currents, and the sum of the two must be IA. So when V in is 0, when these two are connected together, there is no unbalance. This current is the same as this current, and this, as you can see, is a voltage to current converter. That is, in response to application of a signal, two currents are created which differ, the two collector currents. And in fact, the input current here, it's not the actual input terminals that you apply a current. No, you apply a voltage, but effectively this is a V to I converter, voltage to current converter, and the input current can be taken as the difference between these two currents. So what is the difference? Twice X I sub A. Agreed? We will find out what the output current is. V in, we are investigating the DC characteristics. V in could be positive, could be negative, so it could be sinusoidal. It is a signal, but we are investigating the DC characteristics. If there is a change in the voltage between these two terminals, what happens? The change, when the change is negligible, it is an incremental characteristic. Pardon me? Where does this circuit fit in? This is where they are connected, from this point and this point. if I call this as the point C and this as the point D, then this is C and this is D. Okay? I didn't want to draw it because it becomes longish here and also becomes complicated. That part of the circuit is basically a voltage to current converter, so I showed it separately.
So,
Yes.
so what's in the circuit that makes these two currents different, X, I, and I?
What is because if you see these two voltages shall be, these two currents shall be equal if the two bases are under identical conditions. Agreed? The base to emitter voltage, base to emitter voltage, if they are identical, they are connected symmetrically, RE. So they should be identical if these two are connected together. As soon as you apply voltage here, an unbalance is created. Okay, so one of the currents increases, the other decreases, but the sum of them remains the same.
Sir, isn't that the DC current flowing in the collectors change?
Yes, that is correct.
But in a DA, like this connection is similar to a conventional DA connection. How is this connection different from a DA? Because in a DA, the ICs don't change. Only an incremental AC is added to the collector.
That is precisely what is happening here. You see, we are considering that first V in is 0, then V in is a very small quantity. Okay, if it is a very small quantity, then obviously the two collector currents will be different. Then this small quantity will make it oscillate between positive and negative. Source. Oh, this IN is not a source in the physical sense. It is the equivalent input current.
Is it the difference of two currents?
It is the difference between these two currents, XIA and 1 minus XIA.
XIA minus IA.
No, XIA.
So is this a DC current or is it an incremental current?
What is IN?
It's a DC. We are investigating the DC characteristic, as we always do. If I plot I out versus I in, the DC characteristic. From this, I'll be able to find out the AC characteristics. Okay, as we had done in the case of a differential amplifier. Now, there is a point here. The difference is not 2XIA plus IA. Okay, plus IA. Okay, minus IA. All right.
So
then we will argue.
I input flowing, sir?
Pardon me?
Where is this I input?
No, it's not a physical quantity. It's a virtual quantity. Instead of putting two currents as the input, we have put two voltages, and they have produced this input current. This is a defined quantity. IN. All right.
So what if it turns out to be minus?
Pardon me?
2XIA minus IA doesn't.
You see, since this is not a physical quantity, we don't care where it is, what it is. All right, we'll come back to this. If this bothers you, forget about it. We'll see at the end. All right. Now, let's go back to this circuit. Let's go back to this circuit. You see, the collector current of Q1, IC1, is equal to IC1 is equal to I1 is approximately equal to IE1, and if beta is large, this is true, and if beta is large, the base current to Q2, you see this current supplies the base of Q2, which will be negligible, and therefore this is approximately equal to IA1, which is equal to XIA. XIA will bring later, but IA1 is equal to IS exponential VBE1 divided by VT. Agreed? This is the relationship between the base emitter voltage and the collector current.
So, is the quantity X always less than 1?
X is less than 1 because the sum of the two, XIA 1 minus XI, that has to be equal to IA.
So there is one problem here because if RB increases,
If
suppose you are applying a V into a differential amplifier.
yeah,
So the collector current, one of the collector current will increase and another will decrease.
decrease, yes.
So in this case, your X should be more than 1.
X is a X cannot increase because the sum of the two currents has to be equal to IA. X cannot be greater than 1. It's a differential pair. Let me go back to this circuit. It's a differential pair. Whatever these two currents are, they must add to IA. And these are the correct directions. And therefore, X cannot be greater than 1. Okay, is this point clear? That IC1 can be written in this form. Similarly,
Is it VBE1 or VBE5?
VBE1. Hold it. You see, it is this current I1. I1 is IC1, and therefore this is related to VBE1 by this relation. In a similar manner, I4, which is equal to I sub C4, can be written as Is e to the power VBE4 divided by Vt. All right, and therefore I1 by I4, no, let's take I4 by I1. I4 by I1 is equal to, one has to proceed very carefully, I4 by I1, if I take the ratio of the two, it is simply exponential VBE4 minus VBE1 divided by Vt. All right. I can write this as exponential. If I interchange B and E, the sign would be negative, and therefore I get VEB1 minus VEB4 divided by Vt. What is the potential of B1? 0. B4 also 0. And therefore, I can write this as e to the power VE1 minus VE4 divided by Vt. Let's call this voltage the voltage difference between the points E1 and E4 as V1, e to the V1 by Vt. Okay? Let's identify where this V1 occurs. V1 obviously is the difference between this potential and this potential. Isn't that right? Difference between the potentials points C and D. Is the point clear? And therefore, what we have produced is ultimately a difference of potential between Q1 and Q2, which is applied to the differential pair Q2, Q3. Isn't that right? Between the two bases is applied a voltage V1. Now let's draw this circuit a little more in a little more simplified manner to emphasize this point, because much depends on this point. But you also notice that all right, we keep this figure I4 by I1 is e to the power V1 by Vt. Let's see where this V1 is. I'll draw this circuit in a little different manner to emphasize this point. Q1 and the base is grounded. This current is I1 and this current is IA1. I1 and IA1 are approximately equal. We also draw Q4 adjacent to it. This current is I4 and this current is IA2. The difference, now let me use a different color. The difference between this point, which was C in the previous circuit, and this point is V1. So let's take this line. This is V1. Okay. This is the identification of V1, the voltage between the two emitters, and we apply this difference to the two transistors connected in a differential pair, Q2 and Q3 alright. I am just redrawing the same circuit, but to emphasize the point where V1 is created and how it is applied to another differential pair. This current is I3 and the common emitter, the emitters connected together, they are connected to a current generator of value I sub E. I will not show the current generator, I don't want to complicate this circuit, but obviously I sub E would be equal to I2 plus I3. Alright. Now, what is the ratio I2 to I3 is? Can you tell me? Just by looking at this circuit without doing any calculation, the ratio of the two collector currents? E raised to the V1 by V2. Absolutely correct. And we have done this analysis earlier also in the case of a differential amplifier. I2 plus I3 is a constant, I2 by I3 is this, therefore the two quantities can be written as, we have done this earlier, this is a side result if you wish to remember. I2 is IE divided by 1 plus e to the minus V1 by Vt, and I3 is IE divided by 1 plus e to the plus V1 by Vt. Okay? The sum of the two is equal to IE. Now, we don't require this result. What we require is that I2 by I3 is e to the V1 by Vt, and this is equal to I4 by I1. I4 by I1 was also equal to e to the V1 by Vt. Alright? You must appreciate Gilbert, the way he arrived at the result. Now look what happens. If this is so, I4 by I1 is also equal to IA2 divided by IA1. Alright? This is also equal to IA2 divided by IA1. Right? And what is IA2? 1 minus X IA divided by X IA. Now this has become too complicated. Let me reproduce the result here. I4 by I1 is equal to I2 by I3 equals to 1 minus X divided by X. Alright, let's add 1 to both sides. Then I get IE divided by I3, because I2 plus I3 is IE. This would be equal to 1 over X. And therefore I3 is equal to X IE. And therefore what is I2? Obviously 1 minus X times IE. Is the point clear? What we have done is that this proportioning of the input currents has now reflected in the inner differential amplifier. The proportioning of the input current XIA and 1 minus XIA has now reflected into a proportioning of the collector currents of the inner differential amplifier. Alright, let's go back to this circuit and see what has actually happened. Let's go back to the original circuit here. This I2 is 1 minus X IA, alright, and I3 is IE, and I3 is XIE. Okay, so what is I1 plus I3 then?
So 1 minus X.
No 1 minus X. So this is
IE plus IE.
X IA plus IE, okay, X times IA plus IE. And what is this current then? 1 minus X IA plus IE. And what is the difference between the two? What is the difference between the two? Let me. Obviously, these two are my output currents. I1 plus I3 and I2 plus I4 are my output currents, and the difference between the two output currents obviously is twice X IA plus IE minus IA plus IE. Okay, let's go. Let's write this down. I1 plus I3 equal to X IB plus IA plus IE. I2 plus I4 is equal to 1 minus X IA plus IE, and the differential output current would be equal to twice X IA plus IE, all right, minus IA plus IE. And differential input current is equal to twice X, what was it, IA minus IA. Okay. Now, where is the reflection of the signal? Obviously, it is in this term. This is the DC part. This is constant. It does not change. What changes is this part. This is constant. It does not change. This is the changing part. Okay, and therefore you can see that a signal dependent current twice X IA gets amplified as twice X IA plus IE, and therefore what is the current gain? Current gain is 1 plus IE over IA. All right. It is exactly similar to the voltage gain of a non-inverting operational amplifier, except that the two ratios are not those of resistances now. They are of two current sources which can be highly stabilized, and this gain can be any quantity greater than 1. In the analysis, we never considered frequency. How could current be affected by frequency? We only considered DC characteristics. All right, we never considered current. We never considered frequency. We didn't have to consider the effect of capacitors and so on. Of course, it would be dependent on the capacitors, but this is the basic principle of current amplification, and since current is the signal, the only constraint, the frequency has come in our consideration. Can you tell me where? Where? We assume that beta is much greater than 1. We cannot quite go to FT, because FT is the frequency at which beta is equal to 1. If beta is equal to 1, obviously we cannot ignore the base currents as compared to the collector currents. This is the only constraint that has come. All right, and therefore if beta is, you can go up to 10, let's say, which will be a frequency close to FT, this circuit can amplify to a frequency much higher than what can be obtained through voltage processing. The question that remains is how to convert this current into a voltage. That's very simple. You go back to the circuit, our original circuit, and all you do is you include a resistance here, RL, and you take the difference between the two voltages. All right. So this is a very simple means of current to voltage conversion. You see, the drop here would be VCC minus I1 plus I3 RL. The drop here, the voltage here would be VCC minus I2 plus I4 RL. and therefore in the difference those DC quantities will cancel out, that IA plus IE, that will cancel out, alright, and therefore you get a voltage which is derived from a current amplifier through a current to voltage conversion. Tomorrow I will first draw the total circuit. I will first draw the total circuit and then look into the op-amp imperfections.